welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as ray optics. We're going to see telescope today. Now, what do we understand by telescope? First of all, let's see this. What is a telescope? A telescope is an optical instrument which is used for viewing distant objects. Right? A telescope is an optical instrument used for viewing distant objects. Fine. Now, when we talk about telescope, there are two different types of telescopes that you have, right? There are two different types of telescope. One is called as an astronomical telescope. What is an astronomical telescope? An astronomical telescope is a telescope which is used to observe heavenly bodies. Used to observe heavenly bodies. Right? And the other is terrestrial telescope. Terrestrial telescope. A terrestrial telescope is used to observe terrestrial bodies. Used to observe terrestrial bodies. Fine. Now let's try to see the working of each one of them. First, let's try to understand an astronomical telescope. What is an astronomical telescope? Now, an astronomical telescope consists of a large converging lens. One lens towards the object is the lens which is there towards the object is called as the objective, and this lens has a very large focal length and a very large aperture. The lens towards the eye is called as the eyepiece. It has small focal length and a small aperture. Fine. Now let's just write this much down before I go ahead. It consists of two converging lenses. It consists of two converging lenses. One lens towards the object is called objective, and this lens has a very large focal length and a large aperture. This lens has a large focal length and aperture. And the other lens towards the eye is called as the eyepiece. Other lens towards the eye is called as the eyepiece. Fine. It has a small focal length and a small aperture. Focal length and a small aperture. Fine. So that's my astronomical telescope. Fine. Do we get this in here? Next, let's see. The working of the telescope can be studied under the following two cases. One, when the final image is formed at infinity. This case is called as the normal adjustment, and when the final image is formed at distance of distinct vision. Fine, do we get this thing clear? I can say that the working of telescope can be studied under two conditions. One, when the final image is formed at infinity, when the final image is formed at infinity, right? This case is called as normal adjustment. This case is called as normal adjustment. And second is when the final image is formed at DDV. When the final image is formed at distance of distinct vision, right? Now let's see the two methods of working of the telescope. I'll explain. That's what I'm going to do, right? First, I wanted to know what are the two types. Now I'll explain each type in detail. First, let's see the normal adjustment working.
So what's a DDV?
Distance of distinct vision. In order for an image to be formed on the retina of the eye, the object has to be kept at a certain distance from the eye. The minimum distance at which the object has to be kept from the eye so that a clear image can be formed on retina is called as distance of distinct vision. Fine, do we get this in here? Now, let's see this. The normal adjustment working. You have a lens here. This is my principal axis, and you would have rays of light which would be coming from infinity. So you will have rays of light coming from infinity, right? After passing through the lens, they will converge to meet at a point. They will converge to meet at a point where you will have an image formed. This is going to be A bar, B bar, which will be a real inverted and a magnified image. Then you have another lens that is placed here. This is my eyepiece. So you would have rays moving straight. You would have three different rays, and the object is at infinity. Here in this case, the final image is also going to be formed at infinity, and here this will converge after passing through the lens. Here is the eye, right? So this would be like the rays are traveling from here, the rays are traveling from here, and the rays are traveling from here, right? So let's assume that this angle is alpha. Rays from a point on a distant object, rays from a point, rays from a point on a distant object, right? They are coming from there. This is how the rays are going to travel, right? After meeting at this, they will move here. Let's assume that this is my objective. This is going to be my focal length of the objective. and this is going to be my focal length of the eyepiece. Fine. Let's assume that the angle which is formed at the center here is say beta. Right, this point is the pole. Okay, now let's try to understand the working of this. Light coming from distant object form a parallel beam and is incident on the objective, right? The objective forms the image A1, B1. This image is real and inverted. The eyepiece is adjusted in such a way that the image A1, B1 lies within its focal plane, right? And the eyepiece forms a final image which is again at infinity. Fine, do we get this thing here? So, the working of astronomical telescope under normal adjustment. Light coming from a distant object form a parallel beam and is incident on the objective right. Second, the objective forms the image A1, B1 at its focus. So light comes into the objective forms the image. Then this image is real and inverted. This image is real and inverted, right? Now the image, the eyepiece is now adjusted in such a way. The eyepiece is now adjusted in such a way that the image A1, B1 lies in its focal plane. That the image A1, B1 lies in its focal plane. Fine. The eyepiece forms a final image which is at infinity. Eyepiece forms a final image which is at infinity. I've just shown you how the working goes on. Now, what will be the magnifying power of the telescope? The magnifying power of the telescope in normal adjustment is defined as the ratio of the angle subtended by the final image, that is beta, at the eye seen through the telescope to the angle subtended by the object at the unaided eye when both the images are at infinity. So it is nothing but alpha. So it is nothing but your ratio of beta to alpha. So let's write this definition down. I can say that magnifying power of the telescope in normal adjustment is defined as the ratio of the angle subtended by the final image at the eye as seen through the telescope the telescope to the angle subtended by the object, to the angle subtended by the object at the unaided eye, when both the object and the image are at infinity. When both the object and the image are at infinity. Fine. So that's the magnifying power. Now, I can therefore say that since the object distance is very large, it can be assumed that the angle subtended by the object at the objective is the angle subtended by the object at the eye. Whether I look at the object through naked eyes or I look at it through the objective, the angle subtended is going to be the same, right? So I can therefore say that this angle, I can say that the angle subtended by the object, angle subtended by the object at the objective is angle A is going to be nothing but alpha, right? Now the angle subtended by the image at the eyepiece, angle subtended by the image at the eyepiece is beta. Therefore, I can say that as the eye is very close to the eyepiece, I can say beta can be treated as the angle subtended by the final image on the eye. Therefore, I can say that magnifying power is nothing but beta upon alpha, multiply numerator and denominator by tan. So this is going to be nothing but tan beta upon tan alpha, right? Now, since alpha and beta are very small, first of all I can say that magnifying power alpha, guys, can you see the figure? If this angle is alpha, vertically opposite this angle will also be alpha. Tan is nothing but opposite upon adjacent. Tan is nothing but opposite upon adjacent. So I can therefore say that this is going to be tan alpha. Similarly, tan beta is, this is beta. So opposite upon adjacent. So I could say that this is nothing but A bar B bar for beta. Tan beta is going to be A bar B bar upon, we call this as P bar. So this is going to be P bar B bar. The principal focus, the pole of the eyepiece, I'm calling it as P bar, right? Similarly, this is going to be tan alpha is going to be A bar B bar upon PB bar, right? A bar B bar gets cancelled, denominator of denominator becomes numerator. So it is going to be nothing but PB bar upon PB. Now PB bar is nothing but F0 and P bar B bar is nothing but Fe. So the magnifying power of the telescope, astronomical telescope in normal adjustment is nothing but focal length of the objective upon focal length of the eyepiece. Right? Do we get this in clear? So where F0 I already told you is the focal length of the objective and Fe is the focal length of the eyepiece. So in normal adjustment, the distance between the objective and the eyepiece, the distance between, guys, from the figure it's very clear that the distance between the objective and the eyepiece is nothing but f0 plus fe. The distance between the objective and the eyepiece is nothing but f0 plus fe. Thus, if I want to increase the magnifying power of the astronomical telescope in normal adjustment, it can be increased by using a larger focal length of the eyepiece and larger focal length of the objective and a smaller focal length of the eyepiece. The bigger this ratio is, the more will be the magnifying power. That means if I want to increase this magnifying power, I should use an objective of very high focal length and I should use an eyepiece of extremely small focal length. That will give me very high magnifying power. Fine, do we get this in clear? So we've understood normal adjustment. Now, in general practice, the objective is nothing but the achromatic doublet. Now, what do you mean by this? The eyepiece consists of two plano-convex lenses, each of focal length f, which are separated from each other. So, I'll teach you this later. Why do we have to have two different eyepieces? So that we can reduce the chromatic abbreviation and spherical abbreviation. These are two defects that are there of the lens. So, but what we have here is that all you need to remember is that the focal length of the objective should be very large and eyepiece should be very small. Only then you can have maximum magnification taking place, right? So this was in normal adjustment. So do you understand normal adjustment? Nice. Let's see how do you work when the final image is at DDV. Final image at DDV, distance of distinct vision, right? How does the lens work, or how does the microscope work? Now let's see this. You will have objective, principal focus, rays of light coming from infinity, right? After passing through the converging lens objective, they will converge to meet at a point. So they are going to converge to meet at a point. This is going to be my real and inverted image, right? Let's call this as AB. Let's assume that the angle subtended by the object is alpha. This point is say P. Okay, so this is how the rays of light have traveled so far. Okay, now you will have the eyepiece that is going to be situated here. I want the image to be formed at DDV, so I will have passing through the pole, one of the ray passing through the pole, then you will have another multiple rays coming out from here. So you will have one ray that will be here, another ray here, and from this you would have the image coming out. Right? This is where you would have the object form, and I will have an inverted erect virtual magnified object which is going to be A1 B1. Right? Do we get this in here? This angle that is subtended at the eyepiece, this is my eyepiece, is say beta. Right? Let's assume this center is P bar. Right? So rays of light after coming here are going to move out this way. Fine. So we have the eyepiece objective. This is how here in the previous case in normal adjustment, the image was formed at infinity. Here the image is formed at DDV. If the image is formed at DDV, then it is obvious that this distance has to be the DDV. So this distance is going to be the DDV. Let's assume that this distance from the objective to where the real image is formed is the focal length of the objective. This distance from the image to the eyepiece is distance of the image from the object, that is going to be UE. Fine, do we get this in here? So let's try to explain this. The objective forms an image at a distance of the object at its focus. I can say that the objective, first thing, the objective forms an image at its focus, right? This image serves as an object for the eyepiece. This image serves as an object for the eyepiece, right? Now, AB is the image which is formed by the objective at its focus. AB is the image formed by the objective at its focus. Fine. Now the eyepiece is adjusted so that the image A bar B bar, the eyepiece is adjusted so that the image A bar B bar is formed at D, is formed at a distance of D. Fine, do we get this in here? Now, what will be the magnifying power of the telescope in such a condition? Magnifying power, we know that it is nothing but the angle subtended by the image at the eye to the angle subtended by the object at the eye, same as what it was in the previous case. So the definition still remains the same. So I can say that magnifying power of the telescope is defined as ratio of angle subtended by the image at the eye to the angle subtended by the object at the eye, at the unaided eye, right? When both of them, this is the extra part you have, when both of them are at a distance of distinct vision, right? So therefore I can say that magnifying power is nothing but beta upon alpha. I had already shown you what is beta, what is alpha, right? Multiply numerator denominator by tan, so this is going to be tan beta upon tan alpha, right? So the magnifying power is going to be tan beta upon tan alpha. Okay, can we see the figure please? If this angle is alpha, then vertically opposite this angle will also be alpha, right? So tan alpha is going to be opposite upon adjacent, so it will be AB upon BP. Tan beta will be opposite upon adjacent, AB upon BP bar. Fine. So therefore I can say.
So this will be PB bar.
Which one?
The first one, tan beta.
Tan beta.
The
PB.
tan alpha.
Tan alpha is going to be opposite. Opposite is nothing but AB. And adjacent is PB,
Okay.
right? That B bar is that image that has been formed. That's got nothing to do with alpha, right? So therefore I can say that magnifying power tan beta is nothing but AB upon P bar B upon tan alpha is going to be nothing but AB upon PB. AB gets cancelled. Denominator of denominator becomes numerator. So this is going to be nothing but PB upon P bar B. But PB is nothing but F0 and P bar B is nothing but UE. So the magnifying power of the telescope when the image is at DDV is nothing but the ratio of the focal length of the objective to the distance of the object from the eyepiece. Now I can say that, but for a convex lens 1 upon f is equal to 1 upon v minus 1 upon plus 1 upon u, right? For a convex lens I can say 1 upon f is equal to 1 upon v plus 1 upon u. Therefore I can say that for the eyepiece is a convex lens, 1 upon fe is equal to 1 upon ve plus 1 upon ue, right? Now I can apply sign convention by sign convention. Both the object and the image are to the left. That means both are going to be negative. UE and VE both are negative. UE is negative because it's to the left of the eyepiece. VE is negative because the image is also to the left of the eyepiece, and FE, focal length of the eyepiece, is always positive. So if I apply the sign convention, I'll get 1 upon FE is nothing but minus 1 upon VE minus 1 upon UE. Right? Do we get this thing clear? So in that case, I could say that I could say now UE in itself is also negative. So I'll get 1 upon FE is minus 1 upon VE minus into minus plus 1 upon UE. So in that case I'll get 1 upon UE is 1 upon FE plus 1 upon VE multiply by F0, right? If I multiply by F0, before I do that I can say, but what is VE? VE is nothing but the distance of distinct vision. The distance of the image is nothing but distance of distinct vision. So I'll get 1 upon UE is 1 upon FE plus 1 upon D, right? So I can say that 1 upon UE is D plus FE upon D into FE, right? Reciprocate, so you will get UE is D into FE upon D plus FE, right? Now I can say, but we know that magnifying power is F0 upon UE. I have just found out this has to be my value of UE, so I can say magnifying power is F0 upon D into FE upon D plus FE. Thus you could say that magnifying power is F0 D plus FE, denominator of denominator becomes numerator, D into FE, right? So that will be your magnifying power. Fine, do we get this thing here? So do we understand the working of the telescope? Fine. Now, when you talk about lenses, there are certain defects that a lens may have. There are two different types of defects that you can have. One is called as chromatic aberration and the other is called as, one is chromatic aberration. First of all, let's understand what is chromatic aberration. Now, chromatic aberration, when a white ray of light passes through the lens, it will split into 7 different colors. Each color has its own wavelength, right? Now, since each color has its own wavelength, all the rays of light initially parallel to principal axis after passing through the lens should meet at the principal focus. Instead of giving you a single white point on the principal focus, because of different wavelength, you will get 7 different points at different paths. That means they will not all be formed at principal focus, but at different distances from principal focus. You will have 7 different points that will be formed, right? So instead of getting a single bright white image, you will get 7 images of different colors, right? This defect is called as chromatic aberration. Fine, do we get this thing clear? So is this understood? What is chromatic
You get
aberration?
7 colors or those are not?
The 7 rainbow colors, right? Do we get this thing clear? Now, again, all the rays of light initially parallel to principal axis after passing through the lens should converge and meet at a point. This is possible only if the lens surface is exactly spherical. If there is some irregularity in the lens surface, then all the rays of light after initially passing through the principal axis will not meet at the principal focus, but you will have multiple images formed. Why are multiple white images formed? Because the curvature of the lens is not exact. So all the rays of light initially parallel to principal axis will not converge and meet at the principal focus, but you will have multiple images. This kind of defect is called as spherical aberration. Fine, do we get this thing clear? So do we understand the defects in lenses? Okay, we'll stop this here for the day. Thank you very much.